This video covers the Isocal 6 range of products, our latest and most exciting range. The Isocal 6 range currently comprises of two models. The Callisto 2250, which works from 5 degrees Celsius above room temperature up to about 250 degrees Celsius. And the Venus 2140, which works 55 degrees Celsius below room temperature up to a maximum of 140 degrees Celsius. Although not part of this video, the Oceana 6 offers the same features as the Venus 2140, but with a much greater calibration volume. A comprehensive 8-page catalogue detailing the Isocal 6 range is available free of charge upon request. A datasheet and further information is also available for the Oceana 6. The Isocal 6 range is unique to Isotec, and we have written a patent specification and made a patent application. The first application was submitted on the 5th of January 1999. The unique concept of the Isocal 6 is its flexibility. As its name suggests, it will replace more than 6 calibration products and will do everything that is required, even by the most demanding temperature calibration laboratory. So now let's take a closer look at the operation of the unit. The key to the Isocal 6 is the calibration volume shown here. It has an internal diameter of 35 millimeters and a depth of 160 millimeters. The calibration volume shown here is heated in the Callisto, while it is either heated or cooled in the Venus models. A controller with a 0.1 degree resolution sets the temperature of the calibration volume. Our controller contains dedicated software that makes it more stable than other commercially available controllers. The calibration volume can be used in a variety of ways, and each should be considered on its own. This is an anodized aluminium insert designed to fill the calibration volume. It is drilled with 6 holes designed to accept various industrial temperature sensors and the calibrated working standard. The working standard thermometer can be connected to an indicator built into the Isocal 6, which is called a sight version, or it can be connected to a separate indicator such as Isotec's TTI-1 or TTI-2. In this shot, we can see such a device. This is an Isocal Venus and uses an aluminium insert which has been lowered into the calibration volume. Here is a working standard. This is connected via this cable to a plug which is connected to this indicator, which indicates the temperature inside the insert. Next to it, we can see a controller. This has been set to minus 25 degrees Celsius, and at the time of filming, it has got down to minus 9.7 degrees Celsius. The second standard, also placed in another of the 6 holes, is connected to a TTI-2 by this cable, and gives us a more accurate indication because the resolution of the small indicator is only 0.1 of a degree Celsius. Once the sensors in the insert are at a stable preset temperature, the industrial temperature sensors are compared to the working standard thermometer. This is called calibration by comparison. This illustrates a Venus setup as a metal block calibrator, comparing industrial temperature sensors to a working standard. As well as the accuracy of our working standards, we need to know the temperature stability and the vertical and horizontal gradients of temperature in the insert. We have made and issued an evaluation document. Here are some of the tables from this document to show you the overall performance of this metal insert in the Isocal 6. Here we see the stability of one of the Isocal 6 products, the Callisto. It is working at its maximum temperature of 250 degrees Celsius. It recorded the absolute temperature inside the insert for a period of 30 minutes. The temperature variation is less than plus or minus 0.02 degrees Celsius, 20 millikelvins. This table shows how the temperature inside the metal insert changes as we take the sensor slowly out of the insert. These represent withdrawal distances. This is at the bottom, and this is 6 centimeters up from the bottom of the insert pocket. As you can see, at 30 degrees Celsius, the error in temperature is so small that it is almost negligible. Another thing we need to know about the Isocal 6 insert is the temperature variation across the block. If we put temperature sensors at the bottom of different pockets, what kind of temperature gradient can we expect? This table shows the results of tests carried out at 3 different temperatures, at 30 degrees, 125 degrees, and at 250 degrees Celsius, and the temperature gradients are less than about 20 millikelvins over the whole range. This next table is probably the most complicated to try and explain. Basically, what we are talking about is the temperature changes that occur inside the insert as we put more and more temperature sensors into the insert. This is called the loading effect. There are standard tests that have been designed to measure this, and it really illustrates the importance of making all your measurements inside the insert volume. Here, the worst case is at 250 degrees Celsius. We have no rod. We have the standard thermometer connected to the TTI2, and we read a temperature of 250.357 degrees Celsius. The indicator, which is the on-site version, reads a temperature of 250.2 degrees Celsius. Now we add a rod. This is a solid rod of either copper or stainless steel, with a diameter of 8 or 9 millimeters, and it protrudes from the insert for about 200 millimeters. Eventually it gets to room temperature, and this drags heat out of the insert and changes its temperature from the no-load situation to the loaded situation, about 0.43 degrees Celsius. Our built-in semi-standard connected to our indicator is also going to change in temperature, and this compensates for the loading effect. If you relied only on the controller indication, then that 0.4 degrees Celsius would be a loading error, which would have to be added to the uncertainties. So you can see how very important it is to have the built-in or external measurement of what is happening inside the insert as you put in or take out different temperature sensors. On this sheet, you will see the total combined uncertainty of all the different errors that can come into play while we're trying to do a calibration. I'm not going to go through it in detail. It's basically a worst case. We are right at the temperature limit of one of the products, and if we add up and combine all the uncertainties, we get an uncertainty of about 0.16 degrees Celsius. We double that to give us a 95% confidence level, and we get an uncertainty of plus or minus about 0.33 degrees Celsius. This is worst case, and we can make some other measurements that realistically show the kind of errors that we might expect with good procedures. This last sheet shows how you would normally use a metal block insert. We've got a standard quartz 25.5 ohm thermometer in one of the holes, and we have a typical metal sheath 6 mm diameter sensor in another of the holes. We can make a measurement since both are calibrated at 3 different temperatures. We look at the difference, and the actual difference we get is at worst case 10 millikelvins, that's in oil. If we use the metal inserts, here we get a worst case error of about 0.05 degrees Celsius, 50 millikelvins at 250 degrees Celsius, which is probably the smallest uncertainties ever achieved for a metal insert. This full evaluation report of 24 pages is available free of charge. Just let us know if you'd like a copy. As well as our standard metal insert, we can manufacture one to your specifications. We can even supply you with a blank metal insert. However, there are applications where a metal block is not really the ideal solution. In this case, you can remove your metal block insert and replace it with this container of liquid. This shows the Isocal 6 used in its second mode, which is a highly accurate stirred liquid bath. You can see here a yellow knob. Turn this clockwise first and it switches on the stirring motor. Then it controls the speed of the stirring motor. This stirs the liquid in the liquid bath at different speeds, depending on the viscosity of the liquid being stirred. This gives you constant volume of liquid with a great deal of homogeneity, both vertically and horizontally, for the calibration of odd-shaped sensors and short sensors. Let's now have a look at some of the characteristics of the stirred liquid bath option of the Isocal 6. Most of the parameters used by the stirred liquid bath on the Isocal 6 are quite similar to those used in the metal block bath. With the metal block insert, the absolute stability is very similar, and the radial temperature homogeneity is very similar. What is different, and what is a great improvement in the stirred liquid bath, is the vertical gradients, as you can see here at 250 degrees Celsius. The variation over a 60 mm zone was only 15 millikelvins. This is some 10 times better than the immersion characteristics in a metal block bath. And if you look again at the best accuracies we can achieve from a metal insert versus an oil within the stirred liquid container, we can see that the figures are about 5 times better for the oil bath than the metal block bath. So not only can we calibrate odd and short-shaped sensors, we also reduce the uncertainties by about 5 times. The little stirred liquid bath can be filled with alcohol for low temperatures, water for temperatures between 0 and 100 degrees Celsius, or oil for temperatures right up to 250 degrees Celsius. But that's not all this little liquid bath will do. If you have a calibrated working standard as a reference, it's your job to relate all the sensors you're calibrating to that calibrated standard. But what happens if that calibrated standard is drifting, changing its characteristics? Then all the results relating back to that are in error. As a calibration facility, you must be able to recheck your standard thermometer, and to ensure that your reference thermometer hasn't shifted. The common way to do that is to check the value at 0 degrees Celsius regularly, and if the sensor hasn't changed, then you have no need to recalibrate it. This will actually save you money. One way to do this, using the stirred liquid bath, is to fill it with tap water. Set the temperature just below 0, and start to build up an ice mantle around the outside of the liquid bath. This gives us 0 degrees Celsius, and it gives us 0 degrees Celsius very, very stably. Let me show you. This is one of those really boring but vital charts that we produce on occasions. At the beginning, we have got some definitions for you. So this is 5 millikelvins from here to here, and this is one division which is 5 minutes in terms of time. This test started at approximately 8 AM and finished at 3 PM. And this is the chart recording of the liquid bath, used as an ice water bath in absolute terms. The temperature was about -3 millikelvins, as we were just using tap water. But the stability over that period was something like a fraction of a tenth of a millikelvin, a very, very stable result over the 7-hour test period. But that's not all this little stirred liquid bath can do. It can set the temperature of any of the Isocal 6 baths to just over 100 degrees Celsius. Fill the liquid container with water and actually create boiling point. A similar chart recording is available. It shows the stability of about plus or minus 6 millikelvins at the boiling point of water. The problem with the boiling point of water is that you need to know the pressure very accurately, as the temperature of boiling point changes by about 30 millikelvins per millibar. Here at Southport, we can get changes of typically 10 or 20 millibars, and this means variations of up to half a degree. The methods we use for calibration in this stirred liquid bath are very similar to those used in the metal block bath. We calibrate by comparison, except where we use ice and water or water and steam, in which case they are called fixed points. The fixed points, the steam point and the iced water point, are called secondary points on the temperature scale of 1990. But that's not all the Isocal 6 will do. This view shows 2 fixed point cells. This is the triple point of water, and this is a container that can contain either gallium or indium. Both gallium and indium are fixed points on the new temperature scale called ITS 90. By using very pure materials, very pure water and very pure gallium or indium, we can create a fixed temperature inside the well into which we're going to put the thermometer.